from sloths. I'm also glad that you guys don't do TikTok memes in class anymore. My class who are juniors now, I was having them calculate something in physics, and there's a TikTok meme called "I'm just a girl," and they started using that, and I said, "Nope, not touching that one. Not." Mm-mm. They're like, "No, just say it." They're like, "I'm not. No." Yes.
I FaceTimed her today and she was telling me the story on how Reese got acid on her hands.
Oh yeah. Did she tell you about the water bottle tower? Yeah. There's a water bottle tower. There's a lot of stuff. Uh, I really miss. She was the definition of I'm sorry. Did my face say that out loud?
Yes.
Because I would give them something to do, and she would get this look on her face like I'm not doing that. So it was. I always knew how she was feeling. All right, so let's finish up hybridization and get into molecular orbital theory. Everyone always gets scared when the word theory is attached to it. It's not like I'm making you calculate actual wave functions. We could do the full linear combination of atomic orbitals. We can get it all figured out. I'm still hoping some of you take quantum chemistry with me. Statistical thermodynamics. I'm not answering that question right now. I want you to ponder the situation. No, it's not. So nobody takes it. So what we did sp3 and sp2 hybridization. How many regions of electron density did sp3 need? 4. How many regions did sp2 need? How many regions is sp going to need? 2. Okay, so here we see our ethyne molecule. It's an alkyne because why? The triple bond between the carbons. Okay. Now, we know that every bonding location is going to have to be they're going to have to get a sigma bond, okay? But for a triple bond, what are the other two bonds? Pi bonds. So it's 2 pi's. You get 1 sigma at every location. If you start getting higher order bonds, they're pi bonds. Okay, so we can do this carbon 1 and carbon 2, because remember, we can treat each carbon as its own central atom. So now, looking at each carbon, how many regions of electron density does each carbon have around it? 2. It does not matter the bond order, it's just the location. So a single bond is 1 location, a triple bond is 1 location, a lone pair is 1 location. So you're just looking locationally here. So that means both carbons are going to be sp hybridized. Hydrogens will never hybridize because all they have is a 1s orbital. Okay, so now when we say sp hybridized, so let's look at carbon's valence structure. The core electrons, and the valence structure is 2s2, 2p2. That's 4 valence electrons. These 4 valence electrons have to facilitate the sigma and the pi bonds. And since this is only sp hybridization, that means I'm going to take the s orbital and 1 of the p orbitals. That's going to give me 2 degenerate sp orbitals, and then 2 of the 2p orbitals are left over. Now, pi bonds have to go where? No, where in the hybrid structure there are they going to go? Nope. Pi bonds are always going to be in the leftover p orbitals. So if you don't have leftover p orbitals, you don't have pi bonds. So I know I need two of them. 1, 2. Now I need 2 sigma bonds for each carbon. I happen to have 2 valence electrons left. 1, 2. Your sigma bonds and your lone pairs will go in the hybrid level. And again, especially for lone pairs, that's so that they can actually geometrically get far enough away from other electrons to not destroy the molecule. So sigma bonds and lone pairs go in the hybrid level. Pi bonds have to go in the p level. And of course, down here at the bottom, you see the 2 pi bonds and the sigma bond in the middle. Let's try nitrogen. Okay, so we have a triple bond, so that's sigma and 2 pi's. Let's look at the electron configuration for nitrogen. All right, let's draw the valence structure. All right, so each nitrogen, so you see you have a lone pair and a bonding location. Each nitrogen has 2 regions of electron density. Each nitrogen is sp hybridized. So now, that means I'm going to get my sp orbitals. That's going to leave behind 2 of the 2p orbitals. Each nitrogen has to facilitate 2 pi bonds, a sigma bond, and a lone pair. And it has 5 valence electrons to do it. Let's take care of the pi bonds. They're going to go there. Then 1 sigma bond, that's going to go there. And again, you could put it in the other sp, or it doesn't matter. Which means I'm now down to 2 valence electrons and I need a lone pair. And that lone pair is going to have to go in the hybrid level. Is this starting to make any sense yet? I don't know why those are your electron box structures. So you imagine, like if you have a 2s orbital, you have an upspin electron and a downspin electron. That's paired. For the p's, when you see us do upspin electrons, that's Hund's rule. I can't go back and start pairing electrons until I fill up every orbital with the same spin. And I fill in the 2s before the 2p because that is the off-ball principle. You fill lowest energy to highest energy, which is going to help you to remember when we get to molecular orbital truths. You start filling lowest energy to highest energy, just go up. And I want to show you like why, again, when you can see that like sp uses the s and one of the p orbitals, then it makes sense why I have 2 p orbitals left over for pi bonding. So if I just threw sp at you and you're like, where did the p orbitals come from for pi bonding? Well, they just weren't used. They're still there. They weren't used for hybridization. Let's look at carbon dioxide. Okay, first off, what's missing from this Lewis structure? Lone pairs. Okay. This is going to have 2 types of hybridization. Now, first off, each bond is going to get a sigma and a pi to facilitate the double bond. Carbon, how many regions of electron density around carbon? 2. It's sp hybridized. Each oxygen, how many regions? 3, which makes each oxygen what? sp2. All right. So if you were describing this, so let's look at the oxygen. Let's see. Unhybridized, it's 2s2, 2p4, so 6 valence. Now, if I did the sp2, it's going to give me those 3 hybrid orbitals and one of the oxygen's 2p orbitals left over. And so I need a sigma bond, a pi bond, and 2 lone pairs. Pi bond, sigma bond, lone pairs. The carbon, it's sp hybridized. So that means we're going to get our 2 sp orbitals with the 2p orbitals that weren't used. Carbon needs 2 pi bonds, for 1, 2. And it needs 2 sigma bonds, 1, 2, which takes care of all of carbon's valence electrons. Now, to kind of keep on track of learning our geometry, what generalized molecular formula does carbon dioxide take? Or what? So remember, these are, so carbon is going to be your A, AX2. So you have 2 ligands on the carbon and no lone pairs. Now, that means your N plus M is 2. Your electron geometry will be linear. Since there's no lone pairs on the central atom, your molecular geometry is also linear. We don't do it for those, only for the central atom. Well, yeah, it would be E2 because of the 2 lone pairs. That'd be an awkward one. It's not a general, it's not a formula we have, because if you did that, the oxygen would be AXE2, which is just, it's not a structure we have. But yeah, it would, if that was the central atom, it'd be, you'd have to have E2 for the lone pairs. Now, these next types of hybridization, I want you to know they exist. So, but I'm not really going to do anything. You're not going to get them on exams. You're not going to get them in homeworks, but I want you to know they exist because it's where the new hybrid orbital comes from. So a DSP3, how many hybrid orbitals do you think that's going to make? Well, I get 3 from the P's. S, D, DSP3, 5 hybrid orbitals. And the reason for that, so let's look at this molecule. Oh, there's a mean atom, SB. That would be a good one to throw on a quiz. See, some of the elements, their symbols do not look anything like the name. This is antimony. It is a metal deep in the P block. So now if we were to look at the electron structure for antimony, its inner core is going to be krypton. Then you have 5s2, 4d10, 5p3. And because it ends in 5p3, you've seen a molecule do, you've seen an atom do this before. Which column is that in? What's at the very top of the 5p3 column? It's nitrogen. So it's in that column of the P block. So now what's happening, first off, how many valence electrons does this have? Nope. But but it's an excellent guess based off the structure, because you have 15 electrons outside the core. And so it's a good guess. What we have to look for is our highest principal quantum number. In this molecule, what is the largest principal quantum number? 5. So the n equals 5 level, how many electrons are in that level? 5 valence electrons. So always remind yourself, you have to look for the highest value of the principal quantum number. Don't worry about your SPs, Ds, or Fs. Those are your angular momentum quantum number. So your electron structures, principal quantum number, and then L, angular momentum quantum number. So what we have, 5s, I'm going to do the Ds in a different color to represent these are not part of our valence. And the way I wrote it here, 5s, 4d, 5p, I wrote this in increasing energetic order. If you Google electron structures, you'll see them do like everything in, like you'd see them do 4s, 4d, 4p, then 5s, 5d, 5p. But that's not, I mean, that's just going by the principal quantum number. That's not the energy pattern. Your 5s is lower in energy than your 4d. So I do it by energy. And now here's the trick to this. Now, I have that molecule there. You see 5 regions of electron density. 5 regions has to be dsp3, and I also need 5 sigma bonds. Antimony has 5 valence electrons to facilitate these sigma bonds. Now, what you can tell from this is I'm going to have to take the s orbital, all 3 of the p orbitals, and a d orbital to make my degenerate hybrid orbitals. The question is where does the d orbital come from? I'm not taking one of the 4d orbitals. Those are full. Those are stable. But remember, once you hit quantum level n equals 3, d orbitals are available. They are an allowed quantum state. So what I have is I have an empty 5d subshell. Because at quantum level n equals 5, it's an available state. So when I make these hybrids, I take the s, all 3 of those p's, and one of the 5d orbitals. That's going to give me dsp3. And then, of course, the 5 valence electrons, I need 5 sigma bonds. 1, 2, 3, 4, 5. So I need to have a single electron in each orbital. That way I can facilitate all 5 sigma bonds. Now for some fun. This is an AX5. The electron oh, I'm not going to have room there. No, we don't need that anymore. The electron geometry. So first off, there's 2 positions on this molecule, axial and radial positions. The axial positions are up and down. The radial positions, they'll make a kind of a wheel around the center. So let's look at my radial position. How many ligands do I have in the radial position? 3. And for 3 in molecular geometry, what is the word we use for that? Trigonal. You remember how ammonia was trigonal pyramidal? So this is a trigonal molecule. And then what? Bipyramidal. Because look at it. This is essentially 2 pyramids stacked on top of each other. And that also equals the the molecular geometry, since there's no lone pairs on the central atom. The next one you're not going to like. This is the one that people predominantly mess up, I've noticed. Sulfur tetrafluoride. Now, again, we put in our lone pair. We notice that sulfur has 5 regions of electron density. That means this is dsp3. Sulfur is going to have a valence structure. We have 3s, 3p. Now, here's the issue. Since sulfur is in the 3rd row of the periodic table, we haven't hit any transition metals yet. But we're at the n equals 3 quantum level, which means the 3D orbitals are sitting there empty. So we would take one of those for the dsp3. And of course, we would need 4 sigma bonds and a lone pair in the hybrid level. This molecule, though, is an AX4E. N plus M still equals 5, which means that for the electrons, it's still trigonal pyramidal. But now that we're starting putting lone pairs on the central atom, the molecular geometry changes. This one they call the seesaw. And if you really think about it, so question, look at how this is how the molecule's sitting. Those lone pairs, are those in a radial or an axial position? Radial. So because remember the radial component, the radial ligands have radial positions, or there's 3 of them. Your axial, you only have it up and a down. And again, one of the reasons we do this, and we don't really have the time to go through this, is you need to start taking account of what all your bond angles are. And you put the electrons in a place where they're going to have the least number of interactions. So between radial and axial, you have a 90-degree angle. And so the lone pair has to deal with 2 single bond locations at 90 degrees. However, the lone pair will be at the very least 120 degrees from the other bonds in the radial positions, because it's a 360 circle cut into 3 parts. And so when we're dealing with molecules of 120 degrees or greater, we really don't consider as an interaction. So putting the lone pair in the radial position gives it the least number of interactions. So if you ever had to start taking these apart and placing lone pairs, you need to know the angles of that structure and place the lone pairs where they have the least number of interactions. The final type of hybridization, D2sp3. So again, we're just taking one more orbital. The D2sp3 orbitals, there'll be 6 of them. So here we have sulfur hexafluoride. And so the sulfur, we have a 3s level. 3p level. The 3d level, it stays empty. And so I'm going to take S, all three of the p's, and two of the d's. That'll give me 6 degenerate orbitals. And what do I need? 6 sigma bonds. So I have 6 valence electrons. That allows me to get 6 sigma bonds. Let's talk about this structure. This is an AX6. If your N plus M equals 6, we have no lone pairs on the central atom, which means the electron geometry and the molecular geometry will match. This one can be a little confusing until you get it. This one's called an octahedral. It has 6 ligands on it. Why is it called an octahedral? What does octa sound like to you? 8. There is 8 something. You can't see them. Nope. So let's so you remember how the trigonal bipyramidal was two 3-sided pyramids stacked on top of each other? What does this one look like? 2 4-sided pyramids stacked on top of each other, 8 faces. So if you actually drew out an octahedral crystal, it would have 8 faces on it. Let's look at this one here. Bromine pentafluoride. So look at that. What kind of hybridization is it going to have? U2sp3 has 6 locations of electron density. Your bromine, if you do the atomic electron configuration for bromine, you're going to have a 4s level to a 3d level that's completely filled. You have a 4p level. Then you're going to have, I kind of shoved that in there, but, oh, not 5. The 4D quantum level is available, just doesn't have any electrons in it. And again, why is that 4D quantum level available? Well, because the 3D is full. Well, because we've accessed quantum level n equals 4. We have electrons in the n equals 4 level, so the quantum states from that level are accessible. So again, we would set this up the same way. You're going to get your 6 orbitals, and you'd have to have 5 sigma bonds in a lone pair. Let's talk about the shape of this one. This is an AX5E. The electron geometry is still octahedral. But since we have a lone pair on the central atom, we have a different molecular geometry. Okay, nitrogen, or not nitrogen, ammonia was a trigonal pyramidal molecule. This one, we said the octahedral looked like 2 square pyramids stacked on top of each other. What does this one look like? One square pyramid, and that's why it's called square pyramidal. So through doing this, we got kind of a crash course in molecular geometry, but that's how it works. You figure out the generalized chemical formula, you figure out the N plus M, and that'll tell, and then you look for lone pairs on the central atom, That'll tell you if your electron geometry and molecular geometry match, or if they're going to be different. And really the only way to get good at molecular geometry is just to practice it until you got it in your head. This would be something you would use Quizlet for. You need flashcards for this one. Okay. I'm going to walk you through this one. Here we have ethanol. I thought that was pertinent. So let's look at this molecule. First off, everything's a single bond. So everywhere that there is a bond, we know gets a sigma bond. Okay? There's no double or higher, so there's no pi bonds in there. There's still something missing. Can you see it? Yeah, what about it? Lone pairs. Okay, now, if you were to describe the bonding in this molecule, okay, we have carbon 1, carbon 2, oxygen. I know that carbon 1 equals carbon 2. Each carbon has 4 regions of electron density. It means each carbon is sp3 hybridized. The oxygen has 4 regions of electron density, which means that oxygen is sp3 hybridized. Hydrogens will not hybridize. So the way you would describe this is the carbon-carbon sigma bond. The carbon-carbon bond is formed by sigma overlap between carbon sp3 orbitals. The carbon-oxygen bond is formed by sigma overlap bonding between a carbon sp3 and an oxygen sp3. Now, this doesn't involve bonding, but then you could also say that the lone pairs on the oxygen are in the oxygen sp3 orbitals. Because again, lone pairs have to go in the hybrid level. And that's really how you go about, let's talk about the OH, the CH and the OH bond. This is where it's not difficult once you get it. Hydrogen does not hybridize. So what orbital does it have? S. So which level of S? 1s. So the bonding there, the carbon hydrogen bond is a sigma overlap between a carbon sp3 hybrid orbital and a hydrogen 1s orbital. The oxygen hydrogen bond is a sigma overlap between an oxygen sp3 orbital and a hydrogen 1s orbital. Okay, your turn. This isn't a complex molecule. This is not like we haven't described the bonding yet. We're supposed to describe the bonding. And you will need the hybridization for the oxygens. We'll probably finish this chapter on Monday and get into the next one. Which when we get to chapter 10, we've caught you up on some of the most important stuff in this last semester. And we're on to the lesson 2. So once we get into the chapter 10 and beyond, get your math brain going. And I do apologize ahead of time. I am going to probably end up playing math with you eventually, what the hell, because keep in mind, I am a dork at a Sheldon level. I don't know, like I see things, I'm like, I'm not going to make assumptions that we're just going to solve it. I hate making the assumptions and go, well, but the wall is this because, well, you know, stupid assumptions 1, 2, and 3. Like, no, let's just do the calculus. Mhm. So you want to be going forward. So you can look at that, think of it as S and two P orbitals. You took an S with a two P orbital, it's three orbitals, you have three joints. So 300 orbitals. Yeah. So when you look at this formula here, SP2, so SP represents the orbital and the P orbital. Okay, those two orbitals will be two higher. Okay, SP2, because three orbitals will be that three. Okay. You feel like you got it? Nope. What's funny is you usually get correct answers, but you have no confidence. Yeah, I always say, I always ask if you think you got the right answer. Your answer is always no. Someday, even if you're wrong, just come out with confidence, going, yeah, I knocked this one out of the park. No. See what you need to do. That's when you just keep going. Yeah, I don't care. No, I got it. I'm good. Just be one of those people. Okay. So let's take a look at this. Carbon, how many regions of electron density? Two. So that means carbon is sp. Oxygen, what do we think for the hybridization there? sp2, because you have the bond and two lone pairs. It's three locations of density. sp2. Now, again, you could draw these all out, or you realize, so you say, well, I have to have a sigma bond in each location and a pi bond in each location. So each carbon-oxygen bond is going to occur. You're going to have a sigma overlap bond between a carbon sp and an oxygen sp2 orbital. A carbon-oxygen pi bond occurs, so which orbitals facilitate the pi bonds? Nope. The two p's. So in the sp and the sp2 hybridization, there were two p orbitals that we left over. Those two p orbitals are what's going to cause the pi bonds. So the pi bonds are going to occur between carbon and oxygen two p orbitals. And then, of course, the lone pairs on the oxygens are going to be in the sp2 hybrids. So that's what it means when it says talk about the bonding. Let's do an easier one. Just read the question first. This is a very, very prevalent biochemical molecule. Well, you have a benzene ring in there. So the cyclohexane, you're close. So what you need to do is get rid of the double bonds and have two hydrogens on each carbon. That would be cyclohexane. This one is benzene. And remember, in organic chemistry, so we'll talk about this in like dissolves like. Benzene is a nonpolar solvent. So you use it a lot on like hydrocarbons. So benzene will dissolve your oils and your fats. So your nonpolar molecules. You cannot, so oil and water don't mix. Water is polar. Oil is nonpolar. So let's start looking here. Every single location is going to get a sigma bond. There's 6 of them. Try not to double count things. Now here's a question. Underneath that oxygen, the double bonded oxygen, you just see a little point. In an organic structure, what is that? Carbon. Every time you see a peak or an abrupt end to a line in a organic line structure, it's a carbon. So like you remember how we've been doing, I take ethane, and I don't want to draw on the hydrogens. Propane. So that's how it works. Now, we're going to go back to our double bonds, to pi bond, pi bond, pi bond, pi bond. So you should have 15 sigma bonds and 4 pi bonds. Now, the carbon that I've marked, what is its hybridization? sp2. What about the oxygen? sp3. 2 bonds, 2 lone pairs. So once you start getting these bigger molecules, they're actually not that hard to take apart. Just kind of draw yourself a little map. And now we're going to get to the topic that's going to make you wish we were still doing hybridization. Molecular orbitals. Now, we've been talking about atomic orbitals, sp, d, f orbitals. Now, once all these atoms get into a molecule, they're going to undergo, mathematically, we mock it up as we call it the LCAO method, linear combination of atomic orbitals, where essentially we're constructing linear combinations of atomic wave functions. Now here we still call molecular orbitals because all of your atomic orbitals are going to mix together. You're going to get a new set of orbitals unique to the molecule. So for example, this is just hydrogen, H2. Now you're going to notice you have 2 levels. So you have one of your hydrogens on this. So these tree structures. So for your diatomics, you have one of your atoms on this side, the other atom for the diatomic over here. This is hydrogen A, that's hydrogen B. And you'll notice that there's 2 levels. So the wave function, where you do the 1s plus the 1s, you get a sigma bond. So it's an additive wave function. The other one, molecular orbital 2, you get an antibond. So now we're going to take into account bonding and antibonding energies. So for example, if you have the same amount of bonding and antibonding electrons, you have no molecule because your bond order is 0. Now, notice the symbols for bonding and antibonding. We've been talking about sigma bonds, so that makes sense. So on the bottom there, you imagine the hydrogen 1s orbitals coming straight onto those spheres, coming straight onto each other. Then you form this new structure out of both of the hydrogen 1s orbitals. The antibonding, imagine that the 1s orbitals don't like each other, they're trying to get away. That's why you have the side that's flattened out and just push the electron density over to the other side. But pay attention to the notation. Antibonding levels will always have a star. Bonding levels are going to be sigma or pi. Antibonding levels will be sigma star and pi star. Let's look at the energies. You notice how the bonding level for H2 is lower in energy than the individual 1s orbitals, the hydrogen atoms? What does that mean when this forms a molecule? That lower energy means the molecule would what to the electrons in each hydrogen. Nope. Let's just say, okay, it's something no therapist has ever been able to do for me. Let's stabilize. Yeah. So when you go down in energy, that's a stabilization. The lower energy you go, the more stable you are, the less likely the molecule is to come apart. The higher energy of the antibonding is the destabilization. That's why it's antibonding. We have a thing called bond order. Bond order is going to be your number of bonding electrons minus your number of antibonding electrons divided by 2. So to figure that out, here we have and I left some of the electrons in there. But we have a molecular orbital tree. We're going to do nitrogen. Okay. Nitrogen. So each nitrogen atom is going to give us a 1s2, 2s2, 2p3. Now, the 1s level is core, so that'd be your helium core. We're not worried about that. What we have down here at the bottom is, remember, each side is one of your nitrogen atoms. So this is your 2s level. And now each nitrogen gives 2 electrons at the 2s level. So now I have to fill in the molecular orbitals in the center, lowest energy to highest energy. And I have 4 electrons that I have to use. So I have 1, 2, 3, 4. So you see from this 2s level, we get the equal amounts of bonding and antibonding. So this is not where the bonding is coming from. Let's look at the 2p level. In nitrogen, each 2p orbital going to have 3 electrons or subshell. Now, if we start filling these lowest energy to highest energy, we're going to go 1, 2, 3, 4, 5, 6. Okay. Now, let's look at that. What I'm going to show you now, and we'll talk more about it next time, is the electron configuration of a molecule. Okay. So this is the electron configuration for an atom. For a molecule, we're going to go lowest energy to highest energy. And for nitrogen, it's going to be the sigma 2s, 2 electrons, sigma star 2s, 2 electrons, pi 2p, 4 electrons, sigma 2p, 2 electrons. And so from there, we would do our bond order of bonding minus antibonding divided by 2. Because remember, your antibonding has the star on it. Everything else is bonding. So you in the future, you're going to want to be able to tell the bond order and the magnetism of a molecule just based off this electronic structure. Because we'll talk about that more on Monday and finish this chapter up. You will get this in homework, so so you're going to have to go through the book on it anyway. There's a lot of reading on it in the book to try to help explain this.